Hello and welcome. In this video, we're going to look at parallel resistance. We learned that resistors had two terminals, that their polarity did not matter, which means we can place them either direction. We can place the positive side on this side and the negative on the other side, or we can flip it around. We can do the positive side on this side, negative on this side, and their resistance will remain linear, right? Which means that they're the same resistance either direction. So now we're going to learn about parallel resistors. And we see our first parallel circuit over here where our voltage supply here gives us a positive terminal on top. That's that long line of the battery. And we come up and follow the current around here, and the first thing we hit is this node here. And this node is actually directly connected to the next node without any resistance in between. Right? We see all of these nodes connected together up there. Those all have the same exact voltage potential. So if our voltage source is down here, we should see the voltage source across all of those terminals as well, because there's no resistors in line with them yet to drop voltage. So this is going to provide us with a shared voltage down every branch of our parallel circuit. We see that each of that voltage source is going to go down each one of these branches here, and we're going to share that. So the voltage source is seen across every branch. Now that we know the voltage down each branch, we can compare that to the resistor of each branch, and that will give us the current down each branch. And this is where the parallel circuit really becomes a little complicated, is when we get into current, right? Because we expect current to come up here and flow into this first node, and then it's going to divide. We're going to have some current go down this first resistor path, and then the rest of the current is going to travel across to the next node, and then we're going to have some more current drop down this next path, and then it's going to continue on to the next node, and then so on, right? So each branch gets its own independent current. And so that is what this equation says when we look at our total resistance equation down here. It identifies this relationship between voltage and current, and specifically the fact that the current in the top branch, IT, is going to be the sum of all the different currents in each branch, I2, I3, and I4. Right? So if we add all of those currents up together, we end up with the total current output. And we expect all of that current to flow back out the bottom as well and at our negative terminal here. So it's IT again. Right? So that is our expectations, and that is what this equation says. This equation says that the total resistance is equal to 1 over R1 plus R2 plus R3. Right? And that is all of our Ohm's law squished together into one equation. And what it's saying is that the voltage down each branch is going to remain the same. So anytime they want to identify voltage, they place a 1 there. So what we really have here is a voltage source divided by a voltage source divided by R1 plus voltage source divided by R2 plus voltage source divided by R3. And one more, plus voltage source divided by R4. So instead of placing all those voltages in there, we just put a 1 in for each one of them because we know that they're all the same. And so we can represent it as just a 1. And if we look at this a little bit closer here, we can actually keep going. We can say that voltage over resistance. Well, if we do that in Ohm's law, we get current out, right? So this is actually the voltage source divided by the current 1 plus the current 2, right? Because this voltage over resistance here, plus the current through the third branch, plus the current through the fourth branch. Right? And if we add all of those together, we end up with IT. So we can even replace that one step further here. We can say that the voltage source over all the currents would be voltage source over IT, which if we do that in Ohm's law, we get the voltage source divided by the current equals the resistance. So this should be our total resistance, RT. And that is how we derive this equation. Okay, let us know if you have any questions.